All right, folks, last topic of the day is hydrophilic. Sorry, I think I've called this hydrophobic. It might just be a slip of the tongue. What we're trying to say is hydrophilic interaction, uh, liquid chromatography, or what is called in the literature HILIC, H-I-L-I-C. Okay, HILIC. And we've talked about how these modes are differing based on the composition of the stationary phase and essentially the composition, what makes the mobile phase strong. And the good news is actually we've already seen what we need to see on this. Um, so what I mean by that is that HILIC is it's essentially normal phase, LC, stationary phases with reverse phase LC mobile phases, which sounds like why would that ever possibly work, right? Because we have something that's trying to dissolve polar things and something that's trying to elute non-polar things, and it sounds like that's highly incompatible. We're going to see some mechanisms that make this work, but first let's just remind ourselves normal phase functional groups are things like the cyano group that we saw. Um, Cyanide. If you guys watched the last uh, part of the video, and I could not remember for the life of me, C triple bond N, what that poisonous thing was that kills everybody. Cyanide, everybody. There we go. Um, all right, so diol stationary phases, um, aminopropyl, all the stuff that we talked about for normal phase. And in the reverse phase world, this is pretty exclusively, I don't know, maybe there's some other work on this, but the vast majority is going to be acetonitrile with water, the main mobile phase that we talked about in reverse phase LC. Okay, before I go any further, let me tell you that there is a decent review to read on this, and it's probably worth doing, and I'll tell you why, because this is a relatively new technology. So we're not talking about something that has 100 years of history, and that's why I'm only going to be able to show you in a minute the hypothesized mechanisms by which this works, although they're pretty well accepted hypotheses. Um, yeah, people are still working this stuff out, and that's why it's worth reading relatively recent reviews. So annual review journal called Trends in Analytical Chemistry. It's abbreviated this way, TRAC. Trends in Analytical Chemistry 2012, which would have been 37 and pages 48 through 60. Gives a nice little foundational review on what this HILIC thing is all about. But here's the hypothesized mechanism. Um, that would allow something that seems kind of nonsensical, right? Incompatible stationary phases and mobile phases to actually do anything for you. So here's the hypothesized mechanism. The idea is this. You have a stationary phase. It's a polar stationary phase, functionalized at the surface with, our normal phase type surface functionalization. So here it is. Um, and what you're going to do is you're going to add to that an environment that is a solution environment around it that is acetonitrile uh, plus a small percentage H2O. So we're talking 5–10% water. Here's what happens when you do this, or at least here's what we believe happens when you do this. Here's your stationary phase particle. And instead of just a uniform solution environment out here, what you get is the polar nature of the surface character of this particle attracts the water. You get a thin water layer. So we'll call this an H2O layer. It kind of sticks to the particle. And out here, you get your non-polar solvent, acetonitrile. So it's kind of a neat concept actually that what you've done is you've taken the surface of this particle and you've sort of wrapped it with a liquid. It's not all that different from what Martin and Singe did. The two main differences are this kind of wraps around the particle instead of being kind of impregnated within the particle, and that's good. That means that you get good uh, mass transfer at the surface of the particle instead of having to penetrate into the depths of the particle. And the second thing that's different from Martin and Singe is you still have your, surface functionalized groups here. So these little X's might be our cyanos, might be our aminopropyls, whatever. They have some retention capability. They have the ability to bond to things that get into the aqueous solvent. Okay, that's the component that talks about composition of the stationary phase. Let's just make a note here that what's happening is that analytes are actually experiencing two things. They are partitioning into the water layer, right, the H2O. They're partitioning into here, but they are also experiencing NPLC-like partitioning or binding. Binding really isn't the right word, and I've been using it a lot, so we'll stick with it, but it's not really the right word because these aren't specific binding interactions. They're more like solvation interactions, but whatever. MPLC like binding interactions still with these surface. So basically, it's going to partition out of the acetonitrile into the water, but then it's also going to undergo NPLC with these surface functionalizations. Okay, so that's what's happening here. That's the stationary phase. Let's talk about mobile phase. So here's gradient elution. In HILIC. So as time goes on, here's a nice linear gradient like we've been talking about, percent %B. We know now that this axis is strength of the mobile phase, right? As percent %B goes up. Our A here is going to be acetonitrile, almost universally, and our B is going to be water. And maybe one caveat that we didn't talk about in the other modes. In the other modes, there's really no upper limit here. This percent %B can go all the way up to 100%, no problem. Here, we rarely see this go above, say, something like 30%, 40%, not much higher than that. So the question is, what makes adding water a better, a stronger mobile phase, right? If the idea was the water is just becoming part of the stationary phase anyway, why would adding more water allow us to get a stronger mobile phase? And there's a couple of, again, I'm going to be honest here, hypothesized mechanisms by which this works. So the first thing is that increased H2O disrupts the thin water layer. Right, so increasing the amount of H2O, we have essentially washes the thin layer out, right? And then the other thing that happens is that increased H2O increases polarity. Increasing H2O increases polarity, and that acts on the NPLC-like retention. In other words, you increase water, you disrupt that water layer, you also just do normal phase liquid chromatography. You also start competing, let's say competing for, again, this word that probably isn't the right word, binding on the NPLC particle. Okay, Yeah, just one, make sure I'm covering all my bases here. Just one more thing I should tell you about, which is why people do this at all, right? What problem does this HILIC thing solve? Um, so HILIC is basically designed to solve uh, the problem of small polar molecules. Okay, what is the problem with small polar molecules? Well, we see poor retention of these things by reverse phase liquid chromatography. That's not surprising, right? They're polar molecules, and so they're essentially not interacting as strongly as they would, as nonpolar molecules would with the reverse phase um, solvents, right, that are immobilized onto the particle. Um, and the problem with small polar molecules in normal phase LC is that they're susceptible to adsorption. Polar molecules, so this is in normal phase LC, polar molecules are supposed to be retained by normal phase liquid chromatography, right? So that's not a problem. We do get retention of polar molecules in NPLC, but if you picture one of these NPLC particles, and here's I don't know, uh, a cyano group, right? Remember, we have all these down here that weren't properly derivatized, and maybe they weren't end capped either. It's not uncommon at all to buy columns that don't have any end capping. It's like a feature of fancy columns, right? Large molecules are not going to get close enough to the surface. They're not going to get close enough to the surface because look, here's another um, cyano group, and a large molecule is going to just kind of hang out over here as some kind of like linear polymer or something. It's going to hang out here. But small molecules, well, these bad boys, they can get right down in here and they can do the thing you don't want them to do, right? They can do that adsorption. So HILIC solves this problem, and the application areas where this problem is particularly useful is in metabolomics. So if you're not into your bioanalytical chemistry and you're not into all the omics, metabolomics is the study of essentially all the small molecule products of biological systems. It's also useful in lipidomics. If you know what a lipid is, and you know what omics is, you can figure this out. But basically, the idea is the study of all of the lipid components of biological systems. And lipids are challenging because they're not that big, and they also have this kind of partly hydrophilic, partly hydrophobic property that's nice to have this HILIC type environment. And even in some pharma synthesis type applications where you have some complex mixture of polar small molecules that are all drug candidates and you want to separate them out. All right, folks, we've gone kind of long today. I appreciate your patience with this. That's what we'll say about partition chromatography. Great news. We are basically done with liquid chromatography entirely. So what we're going to do when we come back on Friday is I'm going to want to do a little bit of recapping because we've spent more or less the whole semester talking about one very important thing, and I just want to connect a couple of dots for us. And then we're going to jump right into gas chromatography. And we are moving right along here. We'll be done with this semester in no time. So hope things are going well for everybody. Hope everybody's staying safe. Hope everybody's staying healthy. And I hope you guys are watching these videos because I'm not seeing any comments or questions online. So I hope I'm not just screaming into the void here. But I will have another one for you on Friday. Stay safe, everybody.